Every project eventually needs a configuration, modes, limits, feature enables, and almost all of these start life as a switch. So in this episode, we're going to build switch handling, a clean input layer that can grow without rewriting any logic. Welcome to more Little Man Builds. So let's open our library manager, search for SwitchBank, and hit install. We can now navigate to the include library, go down to SwitchBank, and we can load up the first sketch, the 3-bit simple dip switch. We can select our input port and our board, which is the ESP32S3 development board, and hit OK. So the first sketch is the baseline. We define 3 GPIO pins, then create a SwitchBank for those 3 inputs. These switches are wired to ground, so we use input pull-up. That means an open switch reads high and a closed switch reads low. So pull-up handles the electrical side, it gives the pin a stable default state, and active low handles the logic side. It tells SwitchBank that low means the switch is on. In setup, we call sync. That tells the library this is the starting state, so the sketch does not accidentally report the initial switch positions as new events. Then in loop, everything starts with dip.update. That one call handles the reading, debounce, and state tracking. If something changed, we check each switch with rose and fell. So let's send it over to the ESP32 and give it a try. So that works really well. But at this point, the code only knows that a switch changed. So the next step is to turn the switch pattern into something more meaningful. The second sketch uses the same hardware and active low status as before, but now we include a mode name function. This takes a mode number and returns a readable name. The switch statement maps each possible value from 0 to 7. So before we even look at the loop, we can see the intention of this sketch. A raw dip value is going to become a named mode. In setup, we still call dip.sync to capture the starting switch state. But this time, if the SwitchBank has changed, we add the call dip.value. That packs the 3 switch positions into one number from 0 to 7. Now that number can be printed directly, or in this case, passed into mode name. So instead of treating the switches as 3 unrelated on-off inputs, the sketch treats them as one configuration selector. That is much closer to how dip switches are used in real projects. They usually select a mode, a setting, or a configuration. In our case, this is the first step towards choosing different car modes. So let's see how this works as mode names. So bring in the serial monitor again. And I'm pretty sure you get the idea. But based on the pin position, we can choose the mode. Great. But this version still uses microcontroller pins. For 3 inputs, that's fine, but for 8, 16, or a project that's rapidly running out of pins, we need a better way to scale. So the next sketch moves the pins onto a port expander. We have 3 parts, the ESP32, the MCP23017, and the dip switch. Everything needs to share a common ground, so we can connect the ESP32 ground to the MCP ground, and then the common side of the dip switch also goes to ground. That gives the whole circuit one shared reference point. Next, we power the MCP from the ESP32's 3.3 volt pin. Then we connect the 2 I2C lines. GPIO 8 on the ESP32 goes to SDA, that is the data line. GPIO 9 goes to SCL, that is the clock line. Next, we connect the dip switch. Each switch position goes into one MCP input pin. So A0 becomes expander pin 0. A1 becomes expander pins 1, etc., until we get to A7. And because these inputs are configured with pull-ups, the behavior is active low. When the switch is open, the input reads high. When the switch is turned on, it connects that input to ground, and so the input reads low. So at the top, we add the I2C and MCP libraries. We define the address and the expander pins we want to use. These are the MCP pins that now represent our SwitchBank. Next, we create the MCP object. That object handles the actual communication with the expander. Then the sketch adds 2 helper functions. Now milliseconds returns millis, so SwitchBank has a time source for debounce, and read expander reads one MCP pin and returns the raw level. And this is the key idea. SwitchBank does not need to know what an MCP23017 is, it only needs two things: a way to read a pin and a way to get the current time. So when we create the bank with MakeSwitchBank pins, we pass in the expanded pin list, the debounce time, the pin reading function, and the time function. That gives us an 8-input SwitchBank without using any ESP32 pins. In setup, we start serial, start I2C, and then we try to connect to the MCP23017. If the chip is not found, the sketch prints an error and stops there. After that, each expander pin is configured as an input pull-up. That matches the same switch wiring as before. Open reads high and closed reads low. Then we call setMin poll milliseconds, and this prevents the sketch from hammering the I2C bus too aggressively. Finally, we call sync after the hardware is ready, so the current switch positions become the starting state. The loop should now be familiar. Call update. If something changed, check each switch with rose and fell, then print the switch event. And we can check any of the switches. So let's start with number 1. So there we go. It works really well. So the sketches prove the technical idea. We can read a dip switch, debounce it, decode it, and move it onto a port expander without changing the pattern. So now that dip setting needs a place in our project. So this is where we left the car architecture. Inputs on the left, decisions in the middle, and execution on the right. So far, most of those inputs have been live controls, like the RC and buttons. But a dip switch is different. It is a setting configuration, like which driving mode the firmware should use. The first step is to separate reading from meaning. The McpPublisher stays in the input layer. Its job is purely hardware-facing. Talk to the MCP, sample the pins, and report the health. That is useful, but it's still just the raw state. So now, instead of sending the raw state straight for a decision, we make room for an extra step, an interpretation layer. This is where hardware stops being just pins and starts becoming something the rest of the car can understand. Now the new piece comes in, ConfigPublisher. This is the part built around the SwitchBank library. It takes the MCP input state, applies the switch logic cleanly, and turns the dip selection into something meaningful, in our case, configuration and gear-related intent. So the key shift is McpPublisher reads the hardware, and ConfigPublisher interprets the hardware. One layer says, what are the pins doing? The next layer answers, what does that pattern mean? Once that interpretation exists, we can publish it properly. So now ConfigPublisher outputs onto ConfigBus, becoming a proper system-level signal, something other parts of the architecture can subscribe to and use. And that is really the goal of the episode, not to finish the whole authority system yet, but to take the dip switch input and promote it into a clean, reusable configuration stream. At this stage, ConfigBus is the part we care most about. It is published, visible, and it's something we can debug properly. So by the end of this step, we are no longer just proving that the switches work, we are proving that the decoded configuration exists as a stable architectural output. That is an important milestone because once a signal is published cleanly, it becomes much easier to build the next layer on top of. The control core and the authority bus are still shown here for context, but we are deliberately not fully building that part in this episode. Before we write any software, we need to understand the hardware that is already inside the vehicle. Let's start with the gear shifter. So we've got a bundle of wires underneath, and this is where the car starts to reveal its little secrets. This device actually connects multiple wires together, so my job was pretty simple. Move the selector, test the wires with a multimeter, and find out which wire pairs were connected in each position. As an example, let's switch the multimeter onto its continuity mode. We'll just use orange and blue. When in reverse, it will make the beep. And when it's in any other mode, there's no sound made at all. So the final mappings are as follows. Pink plus black turns on all the lights. I'll switch them on quickly now. Just remember we are dealing with LEDs, so it's important to control the current with a resistor. In this case, I balanced the brightness versus the current and landed on a value of 1.5 kiloohms. If you try this yourself, start with lower voltage, I'm using 5 volts here, and higher resistor values to keep the current low. Orange plus blue gives us reverse, and orange plus yellow connects D1, D2, and D3. Black plus green gives us D1, and black plus red gives us D3. For the breadboard setup, if you watch the Arduino examples, you should already be familiar with the wiring of the dip switch. Here I've connected one side to ground, so in and amongst these wires you can see it's on the ground rail, and the other side to the MCP pins. So I've got here orange, blue and brown going to A0, A1 and A2. For the gear selector, we have gear D3, which is red, going to A3. We have forward, which is yellow, going to A4. D1, which is green, going to A5, and reverse, which is blue, going to A6. Don't worry, you'll also see this again when we update the code, and this is all we need from the hardware at this stage. So the first thing we need to do, as always, is update our PlatformIO.ini file. Now we should also fix this in terms of having some kind of naming convention. Next, we're going to search for the library SwitchBank and apply it to the project. The next file we'll look at is our app.io. Now the file here is where the physical wiring becomes the named hardware. And so what we can do here is place our virtual pin allocations. And then we can also update our input pins. Now you might be wondering how I actually came up with the pin allocations in app.io.h. And the answer is I did not just pick pins because they were nearby. On the ESP32S3, some pins affect boot, some are used for USB, some depend on the exact module, and some are just better left alone unless you really know why you were using them. So before I wire anything, I always make a pin plan, and this table is from part 1 of my ESP32S3 stability manual. It is part of a larger stability series covering the problems that make ESP32 projects reset, crash, refuse to boot, or behave differently once they leave the desk. Part 1 focuses on hardware, power, boot, and pin planning. And you can grab that one for free at littlemanbuilds.com. You can find that link above, or you can also find it in the description. Here we need to add our switch banks. And we'll also put one for our gear selector. Let's chuck in a quick comment here. So we're putting in some context masks indexed by position. By the way, if you're enjoying today's content, smash the like button or please consider subscribing. It really helps me out with the algorithm, and I'd love for you to join our community. And everything else stays the same. So what we're doing here is we're just creating a list of MCP input pins used by the dip switch. And this is instead of handling each dip input separately, the code can loop over the entire dip keys. And this is also true for the gear keys here. We then want to count how many inputs are in each list, so this automatically calculates the number of entries in each array. This would come to 3, and gear count would come to 4. The advantage is that if you later add or remove a switch from the array, the count updates automatically, so it's better than manually writing dip count equals 3 or gear count equals to 4. These sections define bit masks for each gear contact, so the gear R mask would also be equal to 0001. And this would be equal to 0010. This one would be equal to 0100, and so on and so forth. So later the software can store the gear contacts in one small value. So for example, if reverse and D1 were both active, we could say that this would be equal to 0101 instead of having to manage 4 separate values. So the last point is our value masks. Now these create valid masks for the bits within each switch group. Let's take dip count as equal to 3. And so for this, we would suggest that valid dip bits are bit 0, 1, and bit 2. Now the reason this is important is because it's very useful when cleaning or validating values, so it would discard any accidental bits outside the valid gear range. So it's kind of a double check if you like. Now we need to create a new file called ConfigBus. These modes give the parents a lot of options. When the child is really young, we can run the car in RC mode, but as they get older, we can change the dip switch to be in one of these other states. This sets the maximum power available to 40%, but in this mode, we then can't take back control of the car with the remote. The different values here are just the maximum power available for the car. The next step is to add logical gear selection, and we derive that from the physical shifter contacts. So the key here with the latching is that when the car starts, the state for the dip switch is true for the entire session. So if we're in RC mode, that's valid until the ESP32 is switched off or reset. Now, because we've updated ConfigBus, we should also update the buses file. Going over this one more time, this is effectively the software wiring cabinet. So it gives tasks access to shared snapshot instances without scattering global objects all around the project. So with the data type now existing, the project needs a shared bus where the data can be published and consumed. The next step is to go into App Policy. This is all fine, and we can add another line here. But today we'll use a config debug to see the output of our ConfigPublisher. But going forward, we will use an authority router to utilize this data and actually push it somewhere, and that will come in the next episode. We'll also introduce another task called Stack Watch, but we'll go into that in a little bit more detail later. Let's go into MCP view. So this declares a function called level high, and it takes the one argument, so the bits we want to check. So what this function is doing is it's going to say within cache.gpio, we already have a bit mask for what is happening at the MCP pins, and we could say it looks something like this. The mask that we've just created would be equal to 0000, etc., but it's bit shifted 3 times, so it would also be the same value. The result of this is to prove they're exactly the same. The function returns true and proves that the most recent input snapshot is both valid and that the input is electrically high. Now, the reason we have this function is because it gives the rest of the code a clean and safe way to ask about one specific MCP pin without repeatedly doing bit maths everywhere. So now we need a new folder called ConfigPublisher. This will roughly follow what we did with all the other publishers. We start off with a constructor, where we need to construct with reference to the MCP bus and the config bus that we're publishing to. As per the other methods, we have something which reads the MCP. We also need a way to decode both the dip value and the gear bits. So we're taking the bit value and getting back the logical gear or the logical mode value. The same SwitchBank idea could read Arduino pins, an MCP, a shift register, or another source entirely. The library does not care. And that is exactly the kind of separation I want in this project. Here we may see that similar data comes through just with a different timestamp. Hence we ignore anything where only the timestamp field is different. Notice here that we're not saying a.stamp. And that's exactly what I mean by the comment here. The implementation starts by giving the MCP23017 a short chance to come online. That matters because ConfigPublisher depends on the MCP state. If the MCP is not healthy, I do not want to guess the vehicle mode or gear. So the safe behavior is publish safe configuration and enter the recovery path. Once the MCP is available, both switch banks are synchronized. It means we do not create fake edges or fake changes just because the software has started and the debouncer has not yet seen a stable history. Then the dip switch is settled and latched, and this is one of the most important design decisions. So the dip value becomes the boot time mode, but the gear selector, as we said earlier, remains live. So when fill snapshot runs, it uses the latched dip value for the mode, but it reads the current debounced gear value for gear. The decode mode function is simple. It maps the 3-bit dip value into a car mode. Finally, the class publishes config snapshot frames through snapshot RTOS. At that point, configuration is no longer a special case. It is just another snapshot stream in the system. And so that is the main architectural payoff. We have taken physical switch wiring, debounced it, decoded it, timestamped it, and published it cleanly. There's no giant switch statement in loop, there's no random pin checks in the motor code, and there's no duplicated bit masks. Just one focused component doing one job. I just realized that for whatever reason, Git tracking wasn't showing up in VS Code, so to fix this you can press Ctrl-Shift-P and go to Developer Reload window. And now we can see that these files have recently been added. Let's go back into Utilities. I have updated these files mainly with comments. For the debugging file, I've added some mutexes to ensure that it prints correctly, And again, these are all freely available on GitHub, so we won't spend much time on them today. ConfigDebug is just a helper showing us what hardware changes are being made and what the new output is. AppDebug is to help me choose which serial monitor code is running at any point in time. To date, we had shown the button events and also output from the power drive handler. Now I want to bring in the decoded shift configuration and also show you what I think is a cool way to monitor the stack. We also have an enable or disable flag, which gives us the opportunity to print what the stack usage is in the background. With that in mind, we should also add the stackwatch code. This runs some diagnostics on the heap and will give us really useful feedback as to what the usage actually is, and we'll go through this in more detail shortly. So there is one more important support change in this episode. So during functional testing, it became quite clear that the direction and the movement should be separated. So a command saying forward should not automatically mean move forward now. So the control bus now carries an explicit drive enable flag and a drive owner. So the control core is still staying simple. The accelerator button creates a direct drive request. The demo drive direction remains forward only, but the command is clearer. The direction command tells the executor what direction would be used. The drive enable tells the executor whether movement is actually allowed, and the drive owner tells the executor who the command belongs to. And that lets Power Drive Handler stay low level but safer. It can refuse movement when drive is not enabled, it can ramp down before changing direction, and it can require a full stop before handing motion from one owner to another. Now that safety infrastructure is useful now, and it becomes essential in episode 3 when the RC direct and joystick ownership start changing dynamically. Finished with that one. We can now go into Power Drive Handler. So the updates for this episode include consuming the drive enable, consuming the drive owner. We're going to print the owner as either the RC, car, joy, or none. We're going to implement a support owner handover interlock, and there's also going to be a keep direction change interlock. And lastly, we're going to improve the drive debug output by putting a flag as to when or not to show it. So the big point here is that Power Drive Handler should not know about the dip modes, the RC delegation, gear policy, or the authority router, but it should know whether the command is enabled and whether ownership has changed while moving. And so that means that the executor stays pretty boring, but it's much safer. And last but not least, we can close these two and fix the main.cpp. I'm not trying to make the mode and gear control work across the whole vehicle yet. I'm creating the configuration layer that the final decision system will consume. So by the end of this episode, if I look at the software architecture, I now have a clean new stream. Raw MCP pins, SwitchBank, ConfigPublisher, ConfigSnapshot, ConfigBus. That is a complete and useful upgrade on its own. So before we upload this to the ESP32, let's revisit the app display file and demonstrate how stackwatch works. Let's throw this across to the ESP32 and also bring in the camera. And what you'll see is that every 10 seconds, stackwatch is printing a complete picture of exactly what memory is being used across all the stacks. So whether it's one of the publishers, one of our control core, power drive handler, it doesn't matter. Notice there's a warning for the current file, ConfigDebug. And that is because we're printing actively, which is using much more memory than normal. But in this case, this is simply for debug purposes, and I'm not really worried about it. So that's a quick demonstration of stackwatch. It's a bit distracting, so we might quickly remove stackwatch from being displayed. So let's start again. Changing the gear. We have the mode, which is currently RC, even though there's no remote control connected at all, and that's coming in the next episode. We have gear D1 selected. The raw contact readings are reverse is 0, forward is 1, D1 is 1, and D3 is 0. The dip raw is currently 0. The bit field, which is the gear raw 0x06, is currently locked. And what that means is that for the dip switch position, It doesn't matter if we change it right now. It's fixed until the next session. So what I mean by that is if we reset the ESP32, you'll note the new mode is max 100. So the point is, at the start of each session, we can set the car mode we're in. We might want to change the max speed that the child can use, and this can simply be done by resetting the ESP32. So in this case, when we reset it again, they only have a maximum of 55% of the available output at their disposal, which is quite cool. But what we really want is to put this back into RC mode. Now, if we change the gear selector position as well, you can see that now gear D2 is selected, gear D3 is selected. We can put it back into park, or we can put it into reverse, and each of the correct allocations in terms of reverse, forward, D1 or D3 is working well. So SwitchBank is currently giving us the raw bit field and the exact high or low readings that are occurring across the gear selector. So everything is working so far. Now let's change the active view. Let's check out our button view. All the buttons are still working. And again, we can do any combination and it will keep tracking everything as required. The last view we'll look at today is the drive view. So when I press the accelerator, the speed increases, and when I release, it decreases again as per our power drive handler formula. Also noting that we have not included any of our config logic at this stage. So even though we're currently in park, it doesn't have any influence on the accelerator at this point in time. That's all coming in the next episode, so look forward to part 3 to see how everything combines together. What matters today wasn't how many switches we had, it's that all of the decisions weren't locked in, and that's the difference between configuration and control. Switches report, control decides, and execution acts. All of the sketches and the entire project are freely available on GitHub, link in the description. Please consider subscribing and smash that like button. See you in the next one.